All right, welcome back, AP Calc. Today we're going to be looking at discontinuity and continuity. First off, we have to classify the different types of discontinuity that we're going to have. And if we look at number one, it looks like it's making a jump as we go from this little open circle to the closed circle. So this is a jump discontinuity, and that's happening when x is equal to -2. If we go over to number two, it looks like there's probably an asymptote going on at 0. It's going off to infinity on both sides. This is an infinite discontinuity, and that's happening at x equals 0. Number three, what kind of discontinuity do we have here? Again, this one is a hole that's removed. We've got an open circle there. Since it's removed, it is a removable discontinuity. It's also called removable because it's easy to fix. We can remove it just by filling in that hole or taking that point and moving it down there. And that's happening at x equals -2. Number four, see it bounce back and forth? This is an oscillating discontinuity. Oscillating discontinuity at x equals 0. Usually from a sine or a cosine function. That's going crazy when it gets close to some number. Number five, again, is a removable discontinuity. And that's just because it's a single point that is removed, and it's easily removable as well. You can just fill that in, and that's happening at x equals 1. And number six is a jump discontinuity, and that's happening at x equals -1. So that's it for the 4 different types of discontinuities. Let's go to the next part here. I'm just going to be working through the odds on this section because I want my students to work through the evens. So these you're going to have to graph or possibly do some algebra or look at the table on the graphing calculator. So the first one here, you can put in the graphing calculator, although it's kind of misleading because when you do graph it, it looks something like this. So you can definitely tell that there's asymptote going on. But what you can't tell is that there's also another discontinuity. And that's because the bottom here will factor into x plus x and x plus 3. And the x plus 3's would cancel out. So if I was to simplify this, it's going to be similar to 1 over x, which is what I drew here, except there should also be a hole right there at -3. So this one has 2 different types of discontinuities. It has an asymptote or an infinite discontinuity. So infinite happens at x equals 0, and then it has a removable discontinuity at x equals -3. And so what intervals is this continuous? So if I was asking that, it would be continuous from -infinity to -3, union -3 to 0, union 0 to infinity. Again, everywhere except at -3 and 0. I've got to pull those out. Number 9, if you graph this one on your calculator, it's going to look like a little bump here. And the denominator here is never going to equal 0. I mean, if you try to factor it, x squared plus 2x plus 2, you're going to find out that you can't factor it. If you use the quadratic formula, you're going to get complex solutions. So if you graph just the denominator here, that parabola, x squared plus 2x plus 2, you're going to find out it looks something like that. It does not cross the x-axis. There's no real zeros to it. So there's no place that's going to become bad for this rational function. And therefore, it's going to be continuous everywhere from -infinity to infinity. On to the next one. Number 5 is a piecewise function. And it's a piecewise function where the left side looks like a line. It's got a slope of like -2. And the right side is a line at -1. So it could look like that. Of course, we want these to see if they are going to line up or not, or is there going to be a hole or a gap between them. So what we want to do is put in -1 onto each side. So if we put on the left side, we're going to have 0. And if we stick -1 into this function, we're going to end up with -1. So really what happens is it comes down with a slope of -2. It's got an open circle here, and then starts up at -1 and flattens out a little bit. So there is a discontinuity, a jump discontinuity, at x equals -1, and therefore this function is continuous from -infinity to -1, union. It picks up right there in that closed circle, so from -1 to infinity. Those would be the intervals where it is continuous. We use a closed bracket here because it's actually equal to -1 on that side, and it's continuous on the endpoint. Number 13, sine of 1 over x. This is the one that's going to oscillate. So if you graph this, you might have to zoom in with your calculator. Maybe use a zoom trig and zoom in a little bit further. I believe it kind of like wiggles back and forth here, kind of like that. And so you're going to have an oscillating discontinuity, and that's going to happen when x is 0. X equals 0. And so this is continuous everywhere else from -infinity to 0, union 0 to infinity. And number 15, what this one looks like is another piecewise function. It's going to look like this parabola, -x squared minus 2x, almost everywhere except at -2. At -2 it's defined to be 2. So we have a parabola, and almost everywhere it's going to be like this except at -2. So what we want to check to see is, do we have an open circle here, or is this going to fill in the gap? So I'm going to put -2 into the quadratic like this. Of course, you could also do this on the calculator, and that would give me -4 plus 4. That looks like it comes out to 0. So at -2 it should be 0. So if I graph it, it's a parabola. It's going to, at -2 it's at 0, and it's going to look something like that and like that. But this is saying that at -2 this side is going to define it to be up at 2. So what we have here is a removable discontinuity at x equals -2. It's continuous everywhere else, so it's continuous from -infinity to -2, union -2 to infinity. Okay, 17, 18, these go together. So basically for this section, you're going to use the graph here on the left to answer the questions on the right. First question says, find f of -2. So you can read it from the graph. What is f of -2? Here it is. The y value there would be at 0. So this one comes out to 0. Then it says, find the limit as we approach -2 from the right side. So we are approaching -2 from the right, and the limit there would also be 0. So does the limit equal the valuation? The answer is yes, because we got the same value up here and here. And so is the function continuous? The answer is yes, by definition. Now if we go to an endpoint like we are here, and I can tell it's an endpoint because that's the end. There's nothing on the left of this function over here. If we're at an endpoint, then we only have to take the one-sided limit in that case. So 0 equals 0. The limit is equal to the function evaluated at that x value. Then it is continuous. So that settles that part. Find f of 2. If I go to find f of 2 is defined to be down here. Not up here because there's an open circle there. So f of 2 is equal to -1. The limit as f approaches 2, or as x approaches 2, is going to be, what does it get closer to? Oh, it gets closer to 3. Does the limit equal the function value there? No. So is the function continuous? No, it's not continuous. So that contradicts the definition of continuity. So for it to be continuous, the limit has to be the same as the function value at the same x value. All right, the next part here. Is f defined at x equals 3? It's not even defined there, so we can't evaluate it there. So that right away rules out continuity, so we know it's not continuous there. 3 is right here on the inside. It's not defined there, so it's not continuous. But we could make it continuous. We could extend this function, and if we do, what y value would we have to plug in here to fill in this little hole? The y value there would have to be 1, so that's what it's asking for there. What value should be assigned to f of 3 in order to make the extended function continuous? The y value would have to be 1. All right, for this section, basically you can just come up with your own examples as long as you're fitting the criteria here. Here it says we want f of 2 to exist. We want the limit from the right-hand side to be the same as f of 2, but the limit doesn't exist. And there's multiple ways that you can do this. So let's go over here to 2 and just say, okay, we want the limit from the right to exist, and we want that limit to be the same as the function value. So I have to have a solid dot there. So I got to fill that in. And then I have to be able to come from the right side, so just make a curve. Function value coming over there. All right, there's that. But the limit doesn't exist, so that means that I can't have a removable discontinuity because it's filled in there. I could have either a jump or I could have an infinite. So easiest way is just to make it a jump discontinuity. So put an open circle below maybe and have the function go that way. That would fit the conditions. I could have also drawn an asymptote there. I can have a function defined on the asymptote, and it could act asymptotically just from the left side here and approach it. That would be another way to do it. So I could have it defined here at 2, and then define an asymptote there to be at 2, and on this side then it just kind of approaches there, and then the limit doesn't exist either. Okay, down to 21, I want f of x to be continuous for all x except at x equals 1, and it's going to have a removable discontinuity. So you're just making sure that you do what it says. At x equals 1, I want to have a removable discontinuity. So you can draw it anywhere you want. I'm going to draw it up here. Make my function look like that maybe. And you could put another point on 1 if you wanted to, but you don't need to. You can just leave it like that. So there is a function that's continuous everywhere except at x equals 1, where it has a it says non-removable. Hold on, we got to fix that. It has a non-removable discontinuity. I made a removable discontinuity, so we got to change that. So there is a non-removable discontinuity at x equals 1. So it could be a jump, it could be asymptote. So I have to pay attention there to the prefix non. Alright, next page here. We want to find the value for a so that the function is continuous. Again, I'm working on the left side here. And we've got 23, 6x over x squared plus 2x, and that's when x is not equal to 0. And then it's going to equal a when x is equal to 0. So this is a piecewise function. It's going to look like the top everywhere except when x is 0. So one way to do this is to graph the top function, maybe put it in and look at the table. This one, though, is not going to be defined because we would have an indeterminate form. So if I try to put 0 in, I would have 0 over 0. I would have an indeterminate form. But notice we can factor the bottom into x and x plus 2. And then we can cancel out the x's. So really this function should look like 6 over x plus 2. So if you have an indeterminate form, you should be able to rearrange it, do some algebra, in this case factor and cancel out common factors. Now when x is 0, what does this come out to? So if I let x equal 0, let me erase that. X equals 0 means this is going to come out to 3. So that means to fill in the hole, I should let a equal 3. So this is going to equal 3 when x equals 0. That will fill in the hole that this one creates. Okay, 25. Here I have a piecewise function. I have a left side, I have a right side. I need to make sure that these are coming together at the same place. Notice that the x value is 2. So to do these, what I want to do is I want to plug 2 into both functions and set them equal to each other because I want the y value to be the same. So I put 2 into the top. I got 2 times 2 plus 3 equals, and I'm going to put 2 in for x on the bottom. So that's going to give me a times 2 plus 1. Of course, we can write that as 2a plus 1. And if I simplify the left side here, I would have 7. So I've got 7 is equal to 2a plus 1. And solve. And that's going to give me a is equal to 3. Okay. And the last one that I'm going to do, very similar, except now I have a quadratic and I have a cubic. And again, these are coming together at -1. So wherever they come together, that's the x value that you're going to plug into both the functions and set them equal to each other. So on the top, I've got -1 squared minus 3 times -1 plus a. And then I'm going to plug it into the bottom, which is -1 cubed minus -1 squared. So what does that give me? Over here I have 1 plus 3 plus a. Over here I have -1 minus 1. So that gives me a plus 4 is equal to -2. A is going to equal -6. So if I let a equal -6, then this function would be continuous, and the left side and the right side would meet, because I set them equal to the same value, to the same y value. And that's it for this lesson. So hopefully that helps, and we'll see you later. Bye.